So I am now going to continue trying to build a decision tree from scratch. And I'm going to use the information gain criteria in order to find out how to split this decision tree. So earlier on, let me just recap some of the code. The data that we're using is currently binary based, 0 or 1 for the features A, B, and C. And Y is the output variable, which is also binary. Okay, then we can basically split by inputs X and outputs Y. Okay, this is the sklearn decision tree. After we split it by entropy, we should get something like this, where we split by maybe the split firstly by the last feature C, and then after that split by B. So I noticed something in the sklearn split. They basically split by 0.5, which is like kind of the average of the two values. So yeah, so probably we can do like a split by taking the max and the min, and then we just bin them into a certain bin. So let's try to do that. So early on we did the information gain method. So we just calculate the entropy of the parent node. Okay, and then once you split, you just take the average entropy of the children. You subtract away the average entropy from the entropy of the parent. You get the information gain. So if the node is very clean, that means like there's only one class in it, the pi will be like 1 log 1, which is 0, and also 0 log 0, which is 0. So the entropy will be 0 for clean node. Okay, and that's what we want to achieve. Okay, if we want to do like for example, we want to prioritize a split of the branch of the decision tree such that we gain as much information of our outcomes as possible from that split. So this is the information gain criteria. So this is the current tree that's coded. Max depth equals to 2. Then the split will be put here. So right now what I want to do is I want to make this work for continuous variable. So we need to find the best variable to split on and what value to split on. So looking at the sklearn method, you can see that they did 0.5, which sort of hints that they just take the like maybe number of classes as the bins, number of maybe unique values as the bins for the split. Okay, so perhaps what we can do is we can then take these unique values. Actually, this might already work for continuous variables. Okay, because when we take the unique values, we split on them. It actually sort of gives this. Okay, so I'm just thinking whether or not we need to change anything. Okay, because you might end up with too much to split on, I guess, if we do this. Okay, but maybe this would be sufficient already. I mean, maybe just using the unique values will be sufficient. But I'm thinking of doing something called the binning method. Okay, so maybe we can do, let's see the decision tree classifier, whether there's anything called bins. Okay, looks like there isn't. Okay, but we can do something called bins. So it's like maybe num bins. So when we do bins, it's like we just take the values here. Okay, and then we split based on the bins. So what we can do is like that. Um, So we have this thing called the np.lin space. Okay, then we can start by saying like 0, 10, 100. So it's like you split from 0 to 10 and then you split into 100 different bins. So now we have like let's say 10 bins over here. We can do this np.lin space over here. We can do it. Okay, then instead of doing only unique values, okay, we can just do like, let me just see whether this works first. So like let's say if I do x a dot max, can I do a dot max? Yes. Can I do a dot min? I can. So I can just do a dot max and a dot min to find out, okay, the dot max, dot min. In fact, we can just do it over here. X var dot max, and then we can just do this for, so split into num bins, number of bins. Okay, and then we do num bins, self.numbers. Yeah, so we can do this and then we can split by a value. So let's see whether this works. So indeed, we can split by value a as 0. Okay, in this case, let's say uh, we don't want to split by A. Okay, let's just do a return over here. Okay, continue. Yep. So we can skip A. Let's see whether it splits by C. And indeed, it splits by C. Okay, it means that the way that it's split is already the same way as this. This is actually C. So we have already reached the same entropy as well, 0.918 over here. And this is indeed the best way that we can go about doing this. Okay, so all right, let us see now. Okay, so we have already done this, make this work continuous variables. I hope this works. Okay, maybe one way to find out, okay, is to do this. Let's just do a separate data, and then we just like just randomly put in some data with. So we want to mimic like different kinds of data. We find minus signs. I'm quite curious to see what will sklearn split by. So let's take a look. If I were to do data like that, oh, okay, I think I need to do this thing here. So if I were to do by continuous variables, okay, so let's just put this thing. Okay, if I were to do by continuous variables, so maybe I put this, uncomment this for continuous data. Okay, we can do a continuous variable here. So what we can do is, okay, this one is default, will be binary variables, and then continuous input variables. Okay, let's see with this, my x will be here, my y will be this. What will be my sklearn decision tree? Let's take a look at the decision tree that's output over here, and you can see that, okay, I think it still turns out to be 0.5. Maybe it's not updated. Okay, let's take a look. Yeah, so it now becomes like that, minus 6, 0.75, and so on. So we can see that there's a change in this. Okay, let us see whether we can like sort of replicate this using our DIY method. Okay, so we do have a split. Okay, we split on B with 26.04. So B with 26.04, you should get only the 2. And okay, so let's see. Okay, let's do by this 0 point smaller than 26. Okay, because this one is going to be smaller, equals to 26.0435. Okay, so we do have all the ones. How about the greater than 0.001? So this means that it did not split that well. Okay, it did not split fully, because here this minus 6, you can get the right values over here. So perhaps what we can do is, I don't know, is minus 6 one of the values of the input data? Was, let's see, this is C actually. So they split by C, but over here we did B. So is minus 6 a value for C? No, it doesn't seem so. But we don't seem to get the right entropy here. Okay, or maybe the way we split might be wrong. Okay, so the best entropy is 0.54, and over here the best entropy is also around there. Yeah, it's about 0.5. I mean, if we take a look at this entropy, 0.811 times one third. What's 0.811 times one third? It's about 0.27. Oh, it's actually a lower entropy. We didn't actually get this. So maybe it's because we, okay, let's try again. All right. Okay, maybe there's some issue with this numbins over here. Okay, this one should be numbins. Okay, so this is A. Okay, so let's try this. We split on A. Okay, with the split smaller equals to 0.5. Yeah, it doesn't seem to split very well. So over here, it's well, actually the entropy is the same. Yeah, it's the same. Actually, the split is okay. This split is okay because this split is fine also. It gives you Yeah, it gives you an okay split. But if let's say I were to increase the numbers to maybe 100, what will be the output? Also 0.5. Okay, looks like this numbins method sort of works. After all, we can probably use this numbin methods to do the decision tree. Okay, and I mean if we go back to the original problem of binary inputs, okay, let's see how it does the decision tree. It splits on A, and then we can see that if we split by this, yeah, it splits pretty well. Yeah, so the original one works as well. So this is okay. So now what we want to do is we want to make this work for, okay, this one is done. So what we want to do is we want to recurse this to the maximum depth available. So what we can do is we can basically find a way to implement this self dot split such that we update what we split by on each branch. So firstly, let us do the recursive function for this. So maybe we can just call this define my split, define split self, and then we can have like x, y, next step. And if the depth is greater than next step, okay, then we just return. All right. So we do not want to oversplit beyond the maximum depth specified. Okay, then we need to do this recursive function um, to do the split. So what we can do is, okay, we can split this value. Okay, maybe over here what we can just call is self dot split uh, x y depth. So this function basically, this function splits based on the best split by information gain method. Okay. So what we'll do is we will then update this self dot split with the right splits that we want. Okay, so let's see. I think all this can keep. Okay, so this one is the initial function to call. Okay, we actually shouldn't call the function split because self dot uh tree, let's call it tree recurse. Okay, so we return if beyond the next step. Otherwise, we will continue to do this. Okay, we will do the variables equals to this, and then after we split this, instead of printing this out here, okay, this one we need to we need to change this. Okay, so what we need to do is we need to do the split, and then we need to call the two split function. So we need to call one tree recurse. Okay, we need to call a tree recurse for x and y a, and then a tree recurse for y a x b and y b. Recursively split trees based on the child nodes. Okay, and then we can then like, update the, or we can actually just return this. So when we return the Okay, we need to return the current split. So the current split will be maybe in a bracket. We return the current split, so we return the best split and the best unique best value. Maybe we just call it best value. Yeah, we return the best split and best value here, and then in the format split best split. Then over here will be outcome for child A, outcome for child B. Okay. So if let's say we face a part where we do not need to split anymore, we should return like um, so basically this part here should give you nothing. So maybe you should just return none. Then this part will be none. Yeah. So we can just return this one, and eventually this self dot tree recurse over here we will just get this, because once we keep returning this recursively, we should get the split, and then you recursively do this, and then recursively do this. You can get the splits recursively. Okay, let's see whether it works. Okay, depth is not specified. So where is my depth? So my depth. So this is quite difficult actually. This one is a recursion problem. So I mean, it's something that you get if you do programming enough or competitive programming. So I think this will be quite hard for the students to get actually. But I've seen one solution that managed to do the recurse. So I'm quite happy. Okay, that people are actually trying. Okay, so this recurse function, all right, we need to limit by the depth. So this max depth here, we need to put self the max depth that we can reference the top over here. Let's try again. Depth is not defined. Okay, so we do have a depth term over here. And this term here, we should start with 0. Okay, so over here, we should do depth plus 1. Okay, because we need to say that we have gone one more step down in the tree. Okay, let's see what's wrong now. No attribute called max depth. Tree recurse is not defined. Okay, so um, it is defined here, right? So, oh, but here we need to put self.tree recurse because we are referencing our own function. So we should get a decision tree split division by 0. Okay, so we also need to check, okay, whether or not um, like whether or not the y values, okay, if the node is clean, okay, no need to split anymore. So if length, if y dot value counts, okay, if the length of this, okay, is going to be 1, all right, we also return none. Okay, let's try. Okay, so I should get a split of 2 depths now. Okay, division by 0 now. So okay, is the division by 0 in the entropy method, or is the division by 0 in this average entropy method? So there could be a case where length y is 0. Okay, we could have a split such that the split is, no, is clean or contains nothing. So we also do a condition to check whether y is empty. So we over here we have a split a0, then we split by a0, then split by a0, none, none. Okay, so over here maybe it will be good if we can also like maybe key in the entropy over here so that we get an idea of what the entropy is. So it appears that we keep splitting on this A here, all right, which is not what we want because we do want to make the entropy lower. So there's some error with the split here. So we can split A correctly, but we have not been able to move on to the next variable. So maybe here there's something wrong. Like maybe when I did my three recurse here, something went wrong. So maybe what I should do is to just maybe print out what I'm recursing on. So maybe I just print out print xb yb. So this is my original one. Okay, this is the y, and this is x. Okay, apparently I split and I do not, my x a is not, what's my xb yb? Empty data frame. Yeah, so what I split into an empty data frame. Okay, that's weird. Okay, I shouldn't split into an empty data frame as of yet. I should split into half half. Okay, so this is not done properly. So so let's just print out XA and YA over here. Maybe I just print out the depth as well, so that I know what depth is this talking about. So okay, I need to solve because I cannot really see where this is. So okay, so the depth 0 is here, depth 1 is here, depth 2 is here. So depth 0, it splits like that. Okay, I want to probably print this out separately. Okay, so my XA is here, YA is here, that one here, here. Okay, so it seems that I did not really split correctly. So why is that the reason? So if we look at this x bar min, x bar max, okay, split by 0, which means that 0 smaller equals 0. Oh, is not sure why this is the case because I do split my XA and YA differently, but the entropy for this should be 1, so there shouldn't be. Maybe I should print the entropy as well to see what entropy they split on. So the entropy is 0.9182, which is correct. Okay, but the output here is wrong, okay, because I should be splitting it into like this child A and child B. Maybe I should just print also maybe a child A. Okay, so debugging is the nature of programming, so we have to debug it. So child A seems to be true for everything. Okay, so uh, what is my value though? Okay, let's just print out the value. So I should, oh, my value is 1. Okay, the value is 1, but you see the best value is actually 0 here. But why is the value 1? So, oh, actually this should be best value. That's best value will tell. So the value is 0. So x bar smaller than equals to 0. So let's try that. X A. So it gave me this actually. All right, so I'm not sure why this var gives me separately different stuff. This should be okay. So my XA and YA are split wrongly. Okay, for some reason, this part here is not. I think I know why, because this stuff might already be destroyed. So by the time it comes out here, you don't get XA and YA. So we kind of need to, because of the way we are doing this recursive thing now, we kind of need to like child A, child B, XA, XB, YA. We kind of need to define these variables earlier. So that when you finish the for loop here, they don't destroy this variable, because we need this to appear outside here. Okay, it's still not working. So this is interesting. Why is this all true and all false? We're supposed to get the two child separately. So I'm not too sure why this is happening, because yeah, this is supposed to take in. Oh, I know why. Okay, I did not save the best child. So what should happen is I need to save I need to save the best child also. So okay, we actually don't need this, all right? So we can just do best XA, best XB, best YA, best YB. Okay, then we kind of need to put this. And then over here, we will just need to recurse this with the best XA, best YA, best XB, and best YB. And then I can also like print out like, I understand why it didn't work already, because it went through the X and Y. That was the last iteration with the value of 1. So we need to sort of save this in the earlier loop. Okay, so we see we actually got this one, okay, which is half the data, 001. And then they loop through into that one and split again into two parts. And then we have the other half, which is the, where's the other half? So we split by A, then we split by B. Okay, which more or less gives us a clean split in the end. Okay, all of the splits are clean at the next step. Yeah, only print out one. Yeah, I didn't print out the other half, but yes, it's splitting correctly. The only thing is that now we need to sort of return this with the equal sign here, because we don't need to split so many times. Just now it split 3 times, so we just want it to split 2 times. So yes, we split 1 time. Okay, and then the next branch we split by B, and then we split by B. Let's take a look. Okay, A, B, B. All right, we take a look here. Okay, we need to regenerate the decision tree for this. So we split by A, B, and B. So wait, we give a while. A, B. Okay, this one can be A. Okay, sorry, this is A. This is like C, and this is B. Okay, but in the end, if you get the values are all. Oh, wait a minute. This doesn't give you the right thing. So maybe I need to reload this data. Okay, let's take a look at the reloaded data. Okay, so we split by A, and then after we split by C. So let's take a look. Over here we split by We split by A, then we split by B. Okay, but the outcome is the same. Okay, the outcome everything is pure, so that's good enough. So it means that this actually works. Okay, this method of doing things actually works. So we have done our recursion. Let me just delete away all this. Very nice. So here is A, and then here's B, and then next branch is here. So now we need to do the predict the label for unseen data. Let's do this part. Okay, maybe before we do this first, let's just see how this works for continuous input variables. Yeah, we should get about the same split as the sklearn one. So let's just run this. Okay, so let's see the sklearn. What does the sklearn give us? So it gives us a smaller. This is a smaller than 0.75. Then we have b smaller equals to 25.83. A high hexadecimal. I'm trying to implement the decision tree with information gain from scratch. Yeah. So yeah, I sort of gave this as a bonus question to some students. But to be fair, I haven't coded it out yet. But I know it's not that difficult. Yeah. So I'm trying to code it out right now for the solution. So I thought I might as well do a live coding session. All right. So over here, we do have this best split here. And now let's see whether this corresponds to this same thing. So you see at the end, everything is clean. So let's see whether we can get something like that, something similar. Okay, so we got this A and B. Okay, so I would say that it is a clean split because in the end it became a zero. Yeah. So A 0.5, okay, around the same. And then B is like 1.66. But in the end the entropy is zero. So it means that it's a clean split. So it is good. Over here is none because like the earlier case here is already a pure node. So this looks like it's working. Okay, great. So now what we want to do is we want to predict what the label will be. So actually in the decision tree sklearn itself, there's also a predict function, I believe. So hmm, so is to predict the class for X. So let's try to do the prediction for this. Okay, so we are doing the predict function. So we take in, okay, so inputs will be label X. Output will be predicted class Y. Okay, maybe I should just comment this also. Calculates entropy based on label distribution, label Y distribution. Okay, then this one will be to splits based on the best split. Okay, and this one will be to fits the tree, fits the decision tree based on the initial um, inputs X and outputs Y. Okay, so we have these few functions. I think all these are okay. Now we just do the predict function because we want to sort of predict what the decision tree um, predict based on whatever we fit here. So we do have this self dot split thing that we have here that tells us the split. So if you look at this first part here is like your first split. It's something like here. This is the first box. Then you go into left and right, true or false, right? So when you go down to true or false, you go down here. So you have your second split here, and then you have the two end nodes here, and then you have your third split here as well. So yeah, we can interpret this, okay, by simply just going through the self dot split function. Okay, so what we'll do is like this. Given this x test, okay, this x test, okay, must have, let's just call it x. Okay, this x test or this x must have the same attributes as your earlier one. If not, your split would make no sense. Okay, so we do have all this over here. So let's just copy and paste this here. So maybe I copy and paste the whole thing. Okay, so we need to like okay, maybe what we'll do is like that. Uh, we actually kind of need to recurse. Okay, so let's do a recurse predict function here. Okay, then split. Okay, so this split will tell us this split will tell us what is the current node that we are in. Okay, so what we'll do is we will take this self dot split. Okay, we return this. So what we'll do is like this. We will take this recurse predict, and this split here is the information at the current branch. Okay, so what we'll do is we will do the this split, and then basically this split itself will have two branch A. We'll just call branch one, branch two. Okay, so actually it's like this split branch one, branch two. So this one maybe we call this split info. So maybe split, or maybe no, we just call this thing as mm, decision boundary, decision info, or maybe call this split info lah. Split info b1 b2 equals to split. Okay, this was split into three branches. Okay, then basically we just need to see whether this x variable is it. Okay, so I realized something. Okay, at the end of this split here, we cannot just have none. Okay, we sort of need this to be the actual class itself. If not, we have no way of telling what class information this is. So we need to store the class itself. So if we do not want to oversplit beyond the depth specified, okay, we kind of need to return the majority class here. So like we need to return. So let's put this over here. So we should return the majority class. So we should return the y dot value counts. Okay, so let's see. Data frame, find out most common value, most frequent value. I think there's a way to do this. So dot mode, is it dot mode? Yeah, we will just need the most common value, or we can just do a counter. I mean, we can do a dot mode. Let's see how the dot mode thing works. So let's say if we have xa like that, and then we do a dot mode, what do we get? Okay, so we do get the most common one, and then we can just take the top one like that. Okay, so we can just return this return. Okay, so if this length y is 0, okay, actually it doesn't matter because nothing will come here. Okay, but just to play safe, we sort of need to give a certain value, like even if it's a non null branch after you split, like maybe if you only split one time and then you don't have another branch here, you kind of need a value to give the decision tree to make a decision on. So we should just return maybe just one value. So yes, I'm afraid. Okay, so maybe we should just do this return 0. Okay, if the node is clean, okay, just return default class. Okay, no samples, return default class 0. If the node is pure, okay, return. So we kind of need a default class over here. So self dot default class will be y dot mode. You just take the most common value. Yeah. If the node is pure, just return the yeah. All this also return majority class. Actually, we can just return one class, but we can just keep it simple and just make the code the same. Okay, so let's see what happens when we do this. Okay, I'm just going to comment out this part here because I'm quite interested to see whether this actually can work first. So it should give the value of the class. So it's like either 1, 0, or 1 here. Based on the output of what we get from the split, we should get the class over here. Then we can use this string information to sort of predict the class when we actually run the decision tree algorithm later. So let's try this. So it looks like it's working already. 1, 0, 1. Okay, let's see whether this is correct. So if we split by A, we should get the right side is class 1. Let's see. Right side is class 1. That's correct. Then we split by B. The left side is class 1 and the right side is class 0. So we should get B. The left side is class 1 and the right side is class 0. Awesome. Okay, my decision tree looks like it's working. Okay, now we need to figure out how to do the predict function for this decision tree, and we can call it a day. So let's try to do this. Sorry about this. So we will split at the branch, okay, and then basically we just check whether the value of this x here. Okay, so this x can actually have um, multiple values actually. So this recurse predict, we kind of need to do this for every single x. Okay, let's see how do we do this. I mean, if it's just only one sample, it's pretty simple. You just need to split through the branches. Okay, let's just treat it as one sample first. Okay, just treat it as one sample. I mean, maybe we can do for more later. So what we'll do is we'll do this. Mm, so we kind of need to process this split and like find out where each value lies. So after we do the recursion, okay, we should get to a certain point of the graph. Okay, so if x, so what we'll do is this split info. Okay, this split info will always be there. Okay, so split info will be like variable split entropy, variable split value entropy. Let's just call it value. Variable value entropy equals to split info. Okay, and then what we'll do is we will then take this information and then we will see whether or not this we will see whether this works. Okay, variable value entropy, uh, we see whether the x is it smaller than the value or not. So if x is smaller equals to value, then we will take the chow. Yeah, so let's see. If x smaller equals to value, x variable smaller equals to value, Okay, what we'll do is we will then return this recurse predict. We will return this recurse predict. Self dot returns recurse predict. We return whether or not, okay, we return basically either b1 or b2. So b1, if because b1 means that this is the left side, else b2. Okay, we also need to find out, okay, if let's say the split info here is just of length 1, okay, if we split, okay, if the split information is only of length 1, it means this is the desired class to return. Okay, so this is what we'll do. We'll return this. Okay, then maybe we can just call, we'll just return, we'll predict. Okay, maybe we just, okay, what's x0? Okay, I just want to take this column here, so maybe, hmm, okay, okay, 0, and let's try this. Okay, this is the, so this will give us the first row, missing one positional argument called splits. This one here. Because predict missing one. Oh, I didn't pass in the split. Okay, that was silly of me. So I need to pass in the, I pass in the split, but I did not pass in x. So I should pass in the x as well. Okay, so I think I cannot do this like that already. So we have to do it like this. Next split will be this. Cannot unpack non-iterable numpy object. So this one is non-iterable. Okay, maybe what we'll do is we'll just print out the splits. So we split by this, split by this. Then they say they cannot unpack this one. So we also need to check whether this first part here uh, works. So actually, we don't need to do this split info thing. Okay, maybe what we do is then just return the desired class. If length split, okay, that's it. Object of type length in 64 has no length. Okay, so We make it a list just to make it have a length. All right, so check if data type is a list. So this one is actually a tuple, right? This is a tuple. So we need to see whether this is a tuple. So all right, so we just check whether it's a tuple. Is the desired class, return it. Okay, so I return this predict. I did not return properly because you can see it returns the entire thing. So what I need to do is I need to return, once I return this split, then I return this. Okay, it's not returning the right thing. So when I do this, okay, it's not exactly returning the right value for some reason. I expected this to return a value y, but somehow it's not returning it. So I'm not too sure why. Okay, oh, maybe I'm printing this here. Okay, so maybe I should just print out this split here just to see whether I can. So this split itself is not the correct split. So it turns out that we don't have, we want this to be next split here. So the split that I'm printing out is this whole thing, which is not what I want to do. So let's just print this split to see whether it actually changes. So it doesn't. So it doesn't actually shrink. So that's something weird. Okay, that's something weird because that means this is not being split properly. One, two. I know why, because this is not equals to tuple. So uh, because we actually prematurely terminated the list. Okay, because a list can also be a split. So that is class 0. Okay, so if you look at the original y itself, the first one is class 0. So let's say if my x is maybe class 5, it's a 1, so I should print out 1. So this is 5. So let's see. Okay, here it should print out 1. Okay, good, it's working. So if I do like 4, it should print out 1. If I do 3, it should print out 1. If I do 2, it should print out 0. 1, it should print out 0. Very good. It got the right, it prints out the right stuff. So this means it's correct. Okay, now let's just remove this printing because we want to print all this. Okay, great. So if we come up with some random initialization of the values, it should be able to predict correctly right now. Okay, so now what we want to do is, okay, we want to just make sure that, okay, so what I want to do is, I think this is working right now. Okay, based on the split itself, we can do the predict function already. So now I want to make sure that I can do for more than one value of x, because it seems that when we do this recurse predict, we actually use a different part of the split here, which is not exactly what we need. Okay, I mean, one way to do it will be to like sort of reference the right split. Okay, but what we want to do, we do the a little inefficient way. Okay, we will just, okay, look through. Okay, okay, so each of x, right, we'll just return. Okay, we return these values here. So let's say if we were to predict, like, let's say two, one to two. Okay, we take the length of this and then we just do like that. So this will recursively predict for all the different types of inputs. Just do for one itself, too many indexes. Okay, check number of rows in data frame. Because actually this is really just the number of row. Okay, it looks like we can do df.shape 0. Iterate over rows of data frame. Or maybe we can just iterate over the rows. That will make it much faster. df.rows. Wow. So it's so much runtime needed. I guess I will settle for this. Yeah, I'll just iterate over the ilog like that. Yeah, because if I were to do this, I could probably have like another vector to store all the different splits for my x. Then I can just look up all at one go. Okay, but I think I'll just keep it simple. I just recursively do the prediction for each x and then just loop the data together. So you can see too many integers. It's very funny. How is that too many integers? Too many indexes. No idea. How is this possible? Self.recurse predict this one. Okay, let's see. Too many indexes. What do they mean though? Okay, maybe what I'll do is I'll just print out this so I get a feel of what does this actually print out. Tree. Okay, so it turns out that the shape 0 is not exactly a good thing to use. Okay, because it put tree, so maybe I need to use something else. I should use index. Let's figure out how to do this. What if I put length for this? It's 3. If I were to do this prediction here, this will give me an error. So I need to sort of make this like this. Then it can give me a shape. All right. Um, guess it's fine. Yeah, we could just use x dot shape. Just need to give the right inputs here. Yeah, fine. Then it will give me like 0, 0, 0, 1, 1, 1. And then if I do for everything, 0, 0, 0, 1, 1, 1. Very good. So it seems that I got the decision tree working. Okay, I think right now what I want to do is to test this out on the, so let me just put here. Looks like this is working. Let us try this on the Wisconsin breast cancer data set. So let's import the data set. So let's do this. From sklearn import data sets. Spin out the data. So data.data and x, y equals to data.data, data.target. Okay. So if we print out y is x, okay, print out y is x, yeah. If we print out y is x, we should get this array here. So if we print out y is y, we should get okay. So in order to just make it clear, okay, we should probably check whether is it a data frame. Check if data type is a data frame. Okay, so we can do this. Make this a data frame if not already one. If not is instance x pd.data frame, okay, then x equals to Okay, we do this for the fit function as well. So that we can make it work for numpy variables as well. So we can split. Now it's splitting. I think for Wisconsin breast cancer data set, maybe I need to split a bit less because like it's taking quite a long time to do this. Maybe the num bins can be a bit less. Instead of 100, we can do 10 bins. So let's just specify 10 bins instead because it might take a while. Yeah, then we can see that it splits over here. Why is there this like name? Okay, so when it returns the class, source of returns it as I think it's fine. Yeah, I mean as long as we are able to predict. Yeah, so we kind of don't want this default class to be like that. Like over here, this one should be the default class. So maybe what we'll do is we do a dot values so that we take out the value instead of putting it as a data frame here. Somehow it's not splitting it correctly. You see over here, like here we still have the name over here, which is not what we want because like we don't want all this over here. So you know what, I'm just going to put all this as values. I don't know whether this will help. There we go. So this is the we can predict all of them as arrays. So we kind of don't want this to just be one value. So maybe we could just, I don't know, take out value from data frame. Dot value is 0. Okay, I'll just take the dot value 0. I hope this still works for the normal one. So this will split the breast cancer data set by depth of 2. Okay, let's see whether Okay, let's just run this again. Okay, we don't do the continuous one here. Okay, we just do the normal one, the binary values here. So the decision tree, you can see that this decision tree, why is my y so much? I didn't do the x and y yet. I think I might have okay, yeah, this looks okay. See the decision tree that is generated. Okay, looks fine now. Now let's see my own decision tree and see what happens. Okay, there's something wrong with this dot value 0. Initially, it's not. It's okay if I just take the y dot mode without this value 0. So you probably have to see whether I can maybe do it like that. Okay, somehow it doesn't work. Okay, the value 0 thing, sometimes it doesn't work, sometimes it works. Okay, I got it. So let's do another function just to handle this. So it's getting more and more complicated, but let's just do one more function. Define extract value. If is instance object pd.data frame return object dot value 0, else return object. So instead of having this extra, we can just put, so this will basically just do the extract value if it is a data frame. If not, it will just take the mode. Invalid syntax. Okay, I've got the, yeah, that's quite funny. Why this not fit didn't work? Maybe if I change this to return object, does it work? I have no idea why this suddenly doesn't work anymore. Oh, I didn't do the self. Okay, now I know. Okay, so now if I were to put back this over here, it should base on whether it's a data frame or not. It will just return. Okay, data frame set. Otherwise, just return the. I kind of want to make this thing over here. So let's see my CLF dot split one one. Okay, what is this? Why can't I get rid of this series? Okay, so we should just call it pd.series then. Gosh, so hard to do this. Yeah. All right, so then we can predict the output like that. Okay, this was for the. Okay, let's do for the initial one, the binary values. Okay, yeah, let's just print out y and see what's the issue. It's a data frame. Okay, so why is there an issue with this mode function? All right, so maybe I'll do dot values here. Okay, let's try again. Right, then I don't want this to be an array also actually. So maybe Okay, so if it's an array, I want to flatten it. So I wonder if I need this anymore. Let's just try to return the object and see what happens. Okay, so I return here the array. And what if I do this part here? What will I return? Let's take a look. I return an array. So actually I don't need this extract function anymore. I've solved the issue. I don't need this anymore. Yeah, I just do dot value 0 instead of dot values. Okay, this should do the trick. So now what I need to do is I just need to flatten this. So this will flatten the array, hopefully. Oh no, it's not. Okay, so let's say I have mm, I think it's fine. We can just leave it as an array then. We don't have to flatten it. Okay, let's try again from the beginning. La la la. Very good. 0 0 0 0 0. Oh, this looks different. 0 0 0 0 0 1. Is there only this looks kind of different, right? Yeah, this is kind of weird because I expected this to be split correctly, like not like that. This is wrong. This 0 0 0 0 0 1. So this is a wrong split. Okay, this is the correct split. So if we look at the correct split for this, you should get this. So the entropy here isn't ideal actually. This is not the we split a B as 0. This doesn't lead to an optimal entropy. This is weird because once you split here, you label both as 0. That's wrong already. So there must be something wrong about this. Mm, let's print y just to see how it looks like. zero. So there's a split that doesn't give the best entropy actually. Could it be the number of bins here? I'm not sure. Mm, mm. Suppose give an entropy of zero at the end. You can see here the entropy is still not zero. Alright, so I can't seem to be able to predict this correctly. I'm supposed to get a 0, 0, 0, 1, 1, 1 like here. I wonder is it because of the way I specified this? Maybe if I change this here. No, it's no difference. Yeah, so it means that there's some issue with the algorithm itself. I thought I checked this just now and it worked. So I'm not too sure what changed. Okay, because I didn't change anything here other than the looping, I guess. It's weird. The entropy here should be zero. Yeah, if we look here, the entropy here, after you split one time, the entropy here should be zero already. Why am I still printing out the y here? Okay, so it looks like here it's not exactly working. Maybe if I do the bins to be like 2, I don't know. Does it does it change anything? Maybe there's an issue with this length here. Let's try to find out. Yeah, it's fine. Yeah, the length is fine. But why is it giving the wrong values now? Look, the prediction is wrong. So it'll be 0, 0, 0, 1, 1, 1. Unless I did this wrongly, this is best. Maybe I will just make sure that it's a new data frame. I don't know. Maybe this will increase the runtime a bit, but maybe it's because the data frame itself, the memory is transferred. So we need to make sure that it's correct. No, it doesn't work. Hmm. Yeah, it doesn't seem to find the right split. So like once it splits here, just now it managed to find the right split, but now it doesn't. Very funny. I do 10 splits. The best is 0.666. Okay, something's wrong with this. Let me try to, I don't know, maybe I add one more variable, see how it goes. 0 1 0 1 0 1 1. Okay, that is 0 1 0 1 0. It's slightly different from here. Okay, there may be something wrong with this y dot mode actually. Okay, it's not this default class because I put to 3, it didn't change anything. So it is really just the way the entropy is calculated. It's not split correctly. Like if I were to use the decision tree for this new one, what I should be getting is I should be getting like this 0.5. Okay, this is not clean split. So maybe it's still okay because I don't expect to get clean split here. Okay, but let's say maybe I increase my depth to 3, 0 0 0 1 1 1 0. So almost a clean split. Let's see the scalar if I set max depth to 3. Do I get a clean split? No, I don't get a clean split. This is a difficult split. So actually, it turns out it might be okay. Yeah, it might be okay. But is the split similar to the scalar one? So 0. Okay, then we split by b. Okay, split by b. That's fine. Then we split by, okay, split by b, get 0, and then you split by c. 0 and split by c, correct? 0 and c. So actually, it looks like the method is correct, and the predict function just doesn't predict all correctly in that case. So let's say I were to do max depth of 2. Okay, let's remove that offending variable. Okay, let's remove that last one. We try to split this data. So this 0 0 0 0 0 1, all right? Let's see the sklearn decision tree. How does it do it? So this is depth 3. Okay, we don't need a depth 3 actually. I think a depth 2 would be enough. So let's use a depth 2. Okay, let's use this and see this. Okay, so it is a clean split in the end. So it splits by C, then it splits by B. I think if you split by A and then you split by B is fine also. You split by A, then you split by B, you should be able to split everything. If I split by A, then I split by B. Okay, let's just try this. Yeah, it predicts fine. Okay, so it turns out the sklearn method may not be doing a greedy split after all because they actually might look at it. Splitter equals to best. Yeah, they might actually have a way to check out the best tree because if we split by A first, the next split may not be optimal. So maybe they already have some form of a recursive method to find out whether it's the best split or not. They did not use the greedy method. So the SK1 is even more optimal. So I think there's nothing wrong with the calculation, okay? Because over here, when we split by A or we split, we didn't exactly do the next split entropy and then feedback. We just took a greedy split. Okay, but the sklearn might have done it non-greedily. They might have evaluated all the way to the best split and found the best split before iterating back. So that is quite cool. That means sklearn is more efficient than the method that I'm doing right now. They actually do a non-greedy splitting. Okay, so for now it's okay. We can do the greedy splitting. I think it's fine. Yeah. So the non-greedy splitting um, will involve this part here, not being just like that. Okay, we actually need to save all this and then we just do like a defer search all the way in. So rather than just return this, okay, we kind of need to save the best split. Actually, it's quite easy to implement the sklearn one. We could actually just keep looping until the final entropy and then we just take the lowest entropy, then we just do a backwards. We can actually just do a backwards recursion to find out how to split and then do this. Okay, but I don't want to do this. Okay, so let's just put this. Um, Note the sklearn method does not do splits, does not seem to be doing a greedy split. They evaluate the best possible split, which is fine. Yeah. So I think this is okay. So we can do this here. Okay. So over here we actually didn't have the best split because we split by A, but we could easily do this. Okay, we could easily do this by changing this a bit, making this a bit smaller, equals to. Okay, then we can see that we actually have the best entropy of 0 over here. Yeah, I think we can just do this. I mean, it works for this case, but actually for other cases, there might be other cases. So over here, numbin is 10. We do want to breast cancer data set. See whether this matches. 0, 0, 0, 0, 0. Not bad. Okay, so we can just have a variable like y predict equals to. Okay, what we can do is we can actually do a train test split. Okay, let's do a train test split. Okay, and then we basically just, okay, this one is let's run it on sklearn decision tree. So train test split, we can just do this. Down 0.5 random state is this. Then we can run the sklearn algorithm here. Okay, so let's see the decision tree for the WDBC. Where did it go to? There. Just like that. Then let's see whether we can get a similar one. So it's like about 105.95 and 135. So let's see. 22, right? 27, and here there is 22, but we got 24. But the entropy is like 0.02 and 0.35, which is actually pretty close. Yeah, you see the entropy here was not very good also. So we can see that this actually not too bad. Okay, so okay, we can also do the predict over here. Okay, let's just do on the X train and Y train, and then we just predict on the X test. Okay, and we do the sklearn metrics. Okay, import accuracy score, precision score, and recall score. And then maybe what you can do is like that. Print accuracy will be accuracy score y print. That's the thing. Accuracy score was y through y print. And we just copy and paste this. Okay, not too bad. Okay, then let's just try out this one. And this, we should do a empty.array.flatten so that we can make it similar. Okay, so it looks like I didn't train on the training, so let's just make this the training. And I need to do the testing. Okay. Verdict seems pretty similar. Sklearn, yeah. So I think if we incorporate a form of greedy selection, okay, it might actually perform just as well as sklearn. So yeah, not too bad. Let's just try a different split. Let's write random set of 0. So 894, 91. So this one we perform better actually. Accuracy, precision, recall. It is 27, 27, 27. Let's see how this looks like. 27, 27. Oh, so here's different. Here's like 7. Yeah, but overall, the last entropy is like 0.5, 0.99. Yeah, the final entropy is quite small. So yeah, different methods, different way of doing it, I guess. Yeah, I think this is good. Okay, now let me just run this entire code to just make sure that it's working, and then actually that's more or less it for today. Yeah, I think the this um, self-created decision tree is not too bad. One way to improve it will be to make sure that instead of doing a greedy method, we can actually just recurse all the way to the end of the tree and find out the average entropy at the bottom. Yeah, so that's one thing we could do. Yeah, but overall, this looks like it's good enough already. Okay, and actually that's all for today. Thanks for watching. I hope this was interesting. This turned out to be longer than I expected. I thought I could code the whole thing in half an hour, but yeah, it took 2 hours plus. It's fine. It still felt quite fun. And yep, I'll see you all next time. Okay, bye bye.